Hello, welcome to lecture 14 of our Essentials of Semiconductor Device Physics course. So in this lecture we're going to derive a result that we're going to need in the next lecture, and this result involves the concept of solid angle. And as I mentioned in the previous lecture, this is not a very important result for this course. So if you want to skip this lecture and just take the result we're going to derive for granted, it is okay. But it's not very difficult as well, so I encourage you to watch it. Okay, so let's begin by recalling the definition of an angle theta from basic geometry. So remember that an angle is defined by the length delimited by the angle divided by the radius of the circle. So the angle theta is the length L divided by the radius R. So the definition of solid angle, and we are representing a solid angle by the letter omega here, is similar to the usual definition of an angle, but instead of a circle we have a sphere, instead of a length we have an area. So by definition, the solid angle omega is the area of the sphere delimited by the solid angle divided by the radius of the sphere squared. So you can think of the sphere as being a football or soccer ball, and you can think of the area as being one of these patches. Let's take this patch here, for example, and then the solid angle delimited by this patch would be the area of the patch divided by the square of the radius of the football ball. Now suppose that we consider a small angle delta theta that opens around an angle theta, and in this case the small variation delta theta is given by the distance that is delimited by it, delta L, divided by the radius. So what we want to do in this lecture is to find an analogous expression for this small variation, but in a sphere. So we want to find an expression for a small variation of the solid angle. And to do that, we're going to consider again a sphere and a coordinate system whose origin coincides with the center of the sphere. And we have here a position vector extending from the origin to the surface of the sphere. And we are using the same labels, the same coordinates that are used in polar coordinates. So theta is the angle that the vector makes with the z-axis, and phi is the angle that the projection of the vector onto the xy plane makes with the x-axis. So now we want to find the area that is going to be delimited by the vector when it varies. First, in the theta direction, keeping the angle phi fixed, and then varying in the phi direction, keeping the angle theta fixed. So here I am representing the small variation around the angle theta. And this small variation will delimit distance delta L, just like in the circle case, and we find that this distance is given by the radius of the sphere times the small variation delta theta. Now we want to consider the variation around the angle phi with the angle theta fixed. So this variation has to be on the surface of a cone delimited by the angle theta. So I'm representing this cone here, and you can imagine that the vector moves a little bit to the left and a little bit to the right on the surface of this cone, making the angle theta with the z-axis. Okay, so suppose that the vector starts from this point and then sweeps all the way to this point, covering a variation in the angle phi of delta phi. So in this case, the vector is sweeping a length delta L prime on a circle which is at the base of the cone, and the radius of this circle we are calling r prime. So to make it easier to see the relationship between r prime and r, we can take a look at the situation where the vector is still on the surface of the cone, but now on the zy plane. So it's very straightforward to notice that r prime and r form a right angle triangle, so r prime is r times sine of theta. So now we can use the usual formula for the angle, so we have that delta phi is delta L prime divided by r prime, which is delta L prime divided by r times sine of theta, from which we conclude that delta L prime is r times sine of theta times delta phi. So the area that was swept by the position vector when it first moved around theta and then around phi is given by the product of this distance and this distance. So by definition, the small variation of the solid angle omega is given by this area divided by r squared. So if you use this expression and for using r delta theta for delta L and r sine of theta times delta phi for delta L prime, we see that the two r's will cancel the r squared in the denominator, and we end up with an expression for a small variation of the solid angle around the angle theta and phi. Okay, that's all we need to know about solid angles for our purpose. So let's take a look now at how we're going to use the concept of solid angle and this expression in the next lecture. Okay, so the situation we want to consider in the next lecture is that of a gas of particles, and the velocities of these particles are randomly distributed. So we can imagine that the magnitude of the velocity is fixed. So all particles have the same speed, but the orientation is randomly distributed. So let's first suppose that these particles move in a plane. In this case, we can represent the orientation of the velocity with a single variable, and I chose it to be the angle the vector makes with the horizontal. And let's suppose we have n particles. Now the question we want to answer is how many of these n particles have velocities making an angle theta with the horizontal within the interval delta theta. And imagine that all particles are concentrated at the center, and then we let them go, we let them travel. So some will travel in this direction, other in this, in this, in this. The particles that landed within this distance here were the particles traveling with angle theta within the interval delta theta. So the proportion of this distance to the length of the circle is the same proportion of the number of particles traveling with angle theta within the small interval delta theta to the total number of particles. So this proportion is delta L divided by the length of the circle, 2 pi times r. So the number of particles that we want is the total number of particles times this proportion, and delta L is r times delta theta. They are cancel, and we find that the total number of particles traveling with angle theta within the small interval delta theta is given by the total number of particles times delta theta divided by 2 pi. Now we consider the same situation as before, but we allow the particles to travel in all directions. Now we need to represent the velocity orientation with two variables, and we choose the variables theta and phi as the angles in polar coordinates. And the proportion of particles traveling with angle theta and phi within a small variation of theta and phi is given by the area delimited by these small variations divided by the surface of the sphere, which is 4 pi r squared. And we've just seen that by definition the solid angle is this area divided by r squared. So this area is r squared times delta omega, and so the r squared cancel, and the delta omega is the sine of theta times the delta phi times delta theta. So we're gonna use this expression again in the next lecture, but instead of the total number of particles, we're gonna use it for the distribution of the concentration of particles, but it is exactly the same idea. Okay, so that's it for today, and I see you in the next time when we discuss the diffusion current.